Hello, fellow Africans. We're gonna be looking in this video at the pandemic of coronavirus in Africa, in our beloved continent, Africa. As you probably following the news, we start having some trends that may be not frightening, but I think we start having for a lot of countries, for quite a few countries, the number of cases are increasing and the number of deaths also due to coronavirus are increasing. And if we look first at this graph, which shows the change of cases, the number of confirmed cases with time, and you can see that for the African countries, we start having a trend towards an increase, different from country to country. Especially, there's four countries here in the front, with Egypt, South Africa, Morocco, and Algeria, and Cameroon and Tunisia in the middle, and the rest of the countries, which have more or less 500 confirmed cases. But again, you really have to be careful because the whole pandemic is really moves in waves. If you look at what happens in China, that was in December and January, and then again February and March it was mostly Europe, and March, April is mostly the Americas, and let's hope that we are not going to be the next, and we'll be able to mitigate these increases here. But again, I think it's what's showing here is at least for these four countries, there is an exponential increase in number of confirmed cases. If we look at the latest data with if we look at the latest data with the April 19, and I sort of ordered them differently a little bit. I think one of the criteria here is the number of deaths due to coronavirus. That's, if you look at that, Algeria has 375 deaths. Egypt is a cumulative of 224. Morocco 138, and South Africa 54. Even if in South Africa there are 3,158 cases confirmed, in Algeria, in Egypt 3,032, in Morocco 2,820, and in Algeria 2,629. The discrepancies here is they are due to a lot of factors, one of them being the number of tests that are carried out by each country, but also the health system. I think in terms of deaths, the health system, and also the health state of the people that get infected. If we know that there are some groups that are more sensitive to the coronavirus, especially with old age, but also with cases of people that have diabetes or obesity or some other factors that are really makes it very hard for people to withstand the disease. And looking at these numbers, I think it's these are the relatively low numbers compared to the other continents. However, the question remains is, are we at the beginning of an increase in our continent? Let's hope not. But if we look at a graph here that they generated a little while ago, with the whole global confirmed cases. And what this graph shows is basically, if you look at the number of the global number of cases, you see that we got from from 0 to 1000 in almost 47 days. We got from 1000 to 2000 in about 7 days. And here we got from 5,000 to 6,000 cases in basically just a day. And if we look at the more recent data, it's even faster than that. I think the number of, so that's basically gives you a trend of the exponential increase in cases, at least in the first phase. And we're going to be looking at this in terms of a model that's used in epidemiology. But before we get to the model, let's take a look at how the pandemic relates to the population. So in terms of epidemiology, if we suppose we have first a population of non-infected people, we're gonna call this population as in susceptible. So this is the susceptible population, so the population that can be contaminated. And then we start having some contaminated individuals, or a certain number of these infected people. So this is infected. We're gonna call it I. And once the infected people get in contact with the S, or with individuals from S, we can have transmission of the infection. And that's gonna be with a certain rate that we're gonna call alpha here, which is the rate of transfer from I to S. If you look in terms of time, then we're gonna have the S population will decrease by, if we suppose that we have a 1-1 relation here, so we basically have 3 more infected people and 3 less susceptible people. So that's S. This is S in a certain time T1, and this is I at a certain time T1. But one other factor that also affects the dynamics here is what happens to I. Once we have I, after a certain time, some of the I can also either heal or die. I'm gonna represent them here by green squares, and we're gonna call them just without specifying who dies, who heals, just the recovered population. So if we looked at in terms of the overall population, the overall population, if we call S equal S0 at the beginning and I equal E0, so basically at the beginning the overall population is going to be equal to S0 plus I0, and once we start having some of the R, it's going to be equal to S plus I plus R. So that will represent the whole population. And one of the models that is used in epidemiology and describes nicely the different relations between these 3 groups is called the SIR model. And S is, as you may suspect, is S stands for susceptible, I for infected, and R for recovered. And the model gives expressions for each rate of these populations, and we'll start with first with I, di over dt, the rate of change of I with time, and that depends on how many S are there, how many I are there, and what's the rate of infection there. So it's going to be equal to alpha S times I, but also we're going to subtract the I's that are converted to R. So we're going to use, and that I didn't put it here, but there's a rate, if we suppose that we have a beta, that's the rate of passage from I to R. So that's going to give us alpha Si minus beta. And for S, it's S will decrease, so the rate is negative, and it's negative this rate here, because the number of S, the decrease of S is equal to the increase in I. And similarly for R, the decrease in E is equal to the increase in R. And we can solve these differential equations. We're going to not get into the mathematics of this, but we can solve and find I as a function of time, S as a function of time, and R as a function of time. We're going to use, I'll show you later on, a simulation of these three different variables. But for the time here, we're going to define two more parameters that are important in terms of epidemiology, R naught and I max, and R naught and I max. So if we take a look at again the rate for I is equal to alpha S I minus beta I. If we put I in factor, so that's alpha S minus beta times I. In order for E to increase, this term here should be higher than 0. So alpha S minus beta have to be higher than 0. If we take S at time t equals 0, S equal S0. That's if at the beginning of the infection. So alpha S0 minus beta should be higher than 0, which means basically that alpha over beta S0 minus 1 should be higher than 0. And this quantity here is what we call the R naught. And that's a very important parameter in terms of epidemiology, which is the ratio between the two coefficients for the infection and for the recovery times the initial population, which is as long as we can consider that S is close to S0. And what R0 represents is the number of secondary infections from a primary infection, which basically means that for a given time, how many individuals, one contaminated individual, how many individuals he or she can contaminate. And this is a very well, a very good parameter that's used for not only for the coronavirus pandemic, but it's also used for other infections. If we look at the flu, for the flu viruses, the R naught is generally estimated around 1.5. For the coronavirus, although data are still coming in, but generally it's estimated between 2 and 3, even close 2.5 to 3. We're going to just put it as more or less 2.5, which is, don't compare to the flu. The coronavirus is more infectious. It gives a higher transmission than the flu. If we get back the equation of I and put this value of R naught, 2.5 minus 1 times I. If we solve for I, that gives I equals I0, the initial number, exponential 1.5 multiplied by the time. And this equation really expresses what we saw in the graphs of those of all the African countries, but it's probably a little bit easier on the four countries that for the four countries that gave the highest number of cases currently, which is South Africa, Egypt, Morocco, and Algeria. That gives an exponential increase. We're gonna see that once once we limit once S becomes lower, we can't consider anymore that it's close to S0. The rate will decrease, and it can even go to 0 if the number gets really very low, and the number of recovery also increases. We're gonna look at that in terms of using GeoGebra. We're gonna do GeoGebra. We're gonna do a simulation of I, S, and R as a function of time. But before we get to that, one more parameter that's really important is the Imax. So if we look at what's the Imax, the Imax is the maximum cases for a given time. So this slide was produced using GeoGebra. On the y-axis is the number of cases, and the x-axis is the time. And we have three curves. We have the three populations: the S population, the susceptible population, the green, which is the recovered people that recovered from the infection. And really, the one I'm focusing on is really the number of cases, which is the number of infections, which is here in red. As we increase alpha, we can see that there's an exponential increase, and that's what we're going to see in the graphs that for the different African countries. This is the phase where we are. There's an increase of an exponential increase of the cases. We're going to see later on another slide that shows the whole model, and but at this stage, I just wanted to show you that the model simulates this exponential growth, increase of cases. So for the Imax, in order to find the Imax, what we're going to do is get rid of the variable time. And to do that, what we're going to do is divide the di over dt by ds over dt, so the time will simplify, and this is equal to minus it's alpha si minus beta I over my minus alpha si, which is equal to minus 1 minus, that's plus. We simplify the I, so that gives beta over alpha times 1 over s. And that's basically, if we are looking for the maximum of I, a maximum of I is obtained when this quantity will go to zero. So basically when this is equal to zero. So the Imax will occur when this quantity is equal to zero. I'm not gonna go into the integration. I think there's some YouTube videos that went through that in details, and especially a guy from Cambridge, I think a young fellow from Cambridge that gave nice mathematical development of all of these equations. But there are other ones if you like it. You just put SRR model and you're gonna find a lot of videos that describe exactly the details. If we solve for we solve for the GIGS and we integrate, then we find Imax, the maximum the maximum of infections will occur I plus I naught plus I plus S naught minus beta over alpha times 1 plus log R naught. And this equation will give you I naught is generally known, S naught is known, R 0 is estimated, beta and alpha are also estimated. The ratio beta over alpha, especially alpha over beta, has also significance. We're not going to get into that in terms of epidemiology, but we get an estimate of that. Then we can find what the estimate of Imax. Once we find the estimate of Imax, we can get back to the rate and plug in that number and find which time exactly that can occur, which time will I reach the Imax. Now you have really to be careful when you're looking at, because the way we find these different parameters of the model, we get them from the data, which basically means that we have to use the data we have for each country to find for each country what are these values. And that creates some of the problems, but they're not impossible problems, because ideally what you would like is to test all the population and find exactly who's infected, who's not infected, isolate, etc. That's not possible even in the most developed country, and it's less in our African countries. So what we usually have is data, and we in modeling we work with those data. Basically, most of the data from the African countries, you're getting people that have symptoms and maybe serious symptoms, and we know more or less ranges for how many people get severe symptoms, how many get moderate symptoms, how many are completely asymptomatic. We called one with moderate, we call them also post-symptomatic. So we have ranges for each one of those, and we can correct knowing that what probably we get in the African countries is maybe the most severe, with part probably of the moderate. And we can work with those ranges to derive each and every one of these parameters. And we pretty much can come up with a range for our predictions that can be relatively accurate. And but you have also to keep in mind that it's really because it's based on data. It's a model that we every day you have to try it again as you get more data, and you're really not looking at the evolution from day to day. It's not. It's really looking maybe at 4 or 5 up to a week, when you start having tendencies, the trends, that's really what we are looking for. When you see the numbers either still increasing or the numbers start to stabilize. And we're going to look at that in the simulations that I used for using GeoGebra. And it's going to give you an idea of what's the shape of these curves. This slide shows the whole model. Again, on the y-axis is the number of cases, and on the x-axis is the time. In gray, the S population, which is the susceptible population, people that can be infected. In green, people that healed, they recovered. And in red, that I really want to focus on, is the number of cases we have. And this curve is really important because there's shows a peak, and that peak is really important when it occurs and how high it is. If we take the case that I have here, the dotted line here is supposed to represent the number of beds available for infected people, which I call the hospital capacity, which basically the capacity of the hospitals to treat the infected people. And what we want is that this number should be all the time higher than the number of unaffected people. However, if we increase alpha, what happens is the peak will occur a lot earlier, and it's going to be higher. So basically, the number of people here are people that we can't handle. The hospital capacity can't handle. It's basically people that we can treat because the number is higher, the number of beds that we have available. However, when we decrease the alpha, that number will decrease, and again we hit the peak here. Even at the peak, it's still lower than the number of beds, and that's what's called the flattening of the curve. Even if maybe in terms of cumulative cases, there's not a difference. I think maybe the number of people are going to be the same. The total number of infected people are going to be the same, but the rate at which this occurs allows us to have to manage them with the hospital capacity. So the number of infected people is never higher than the number of beds. We're going to see in the model how we can do that